96%. That is the percentage of actively managed large-cap equity funds that underperformed the S&P 500 over a 20-year period, according to SBIVA data. When a fund manager claims they can beat the market, how do you test that claim with data? You do not just look at their returns and guess. You set up a formal statistical test with a null hypothesis, an alternative hypothesis, a test statistic, and a decision rule. Hypothesis testing is the framework that separates gut feelings from evidence-based conclusions. The CFA exam tests this topic heavily because it is the foundation of every quantitative research finding in finance. If you cannot test a hypothesis correctly, you cannot evaluate any investment research. In this lesson, you will master hypothesis testing for the CFA exam. We start with the structure of a hypothesis test. Null and alternative hypotheses. One-tailed versus two-tailed tests. Then the test statistic and how it is calculated. The decision rule using critical values and significance levels. Type 1 and Type 2 errors, the two ways a hypothesis test can go wrong. The power of a test, the probability of correctly rejecting a false null. P-values and what they actually mean. The relationship between confidence intervals and hypothesis tests. Then specific tests. The z-test and t-test for means. The chi-squared test for variance. The f-test for equality of two variances. 5 exam questions with full wrong answer analysis. Hypothesis testing. Lesson 8 of CFA Level 1 Quantitative Methods. Part 1. The structure of a hypothesis test. Setting up the framework before touching any numbers. Every hypothesis test begins with two competing statements. The null hypothesis, written H sub 0, is the statement you assume to be true until the data proves otherwise. Think of it as the default position, the status quo. In a courtroom, the null hypothesis is that the defendant is innocent. The alternative hypothesis, written H sub O or H sub 1, is the statement you are trying to find evidence for. It is what you believe might be true and want to test. In a courtroom, the alternative is that the defendant is guilty. Here is the critical concept. You never prove the null hypothesis true. You either reject it or fail to reject it. Failing to reject is not the same as accepting. Just because a jury says not guilty does not mean the person is innocent. It means the evidence was not strong enough to convict. The CFA exam tests this distinction. You reject H0 or you fail to reject H0. You never accept H0. The CFA exam distinguishes between two-tailed and one-tailed tests. A two-tailed test asks, is the parameter different from the hypothesized value in either direction? H0 says mu equals mu0. H sub A says mu is not equal to mu0. You reject if the parameter is significantly higher or significantly lower. A one-tailed test asks, is the parameter specifically greater than or specifically less than the hypothesized value? For a right-tailed test, H0 says mu is less than or equal to mu0, and H sub A says mu is greater than mu0. For a left-tailed test, it is the opposite. Why does this matter? Because the same test statistic might lead to rejection under a one-tailed test, but not under a two-tailed test. A two-tailed test splits the rejection probability equally between both tails. A one-tailed test puts all the rejection probability in one tail, making it easier to reject in that specific direction. The exam will specify which type of test to use. Read the hypotheses carefully. The significance level, denoted alpha, is the probability of rejecting the null hypothesis when it is actually true. Think about this carefully. Alpha is the probability of making a mistake, specifically the mistake of saying the null is false when it is actually true. Common significance levels are 0.10, 0.05, and 0.01, corresponding to 10%, 5%, and 1%. Alpha equals 0.05 means you are willing to accept a 5% chance of wrongly rejecting a true null hypothesis. Lower alpha means you require stronger evidence to reject. You are being more conservative. Higher alpha means you accept weaker evidence. You are being more liberal. The significance level is set before you look at the data. Setting it after seeing the data is a form of data snooping that the CFA curriculum explicitly warns against. Part 2. The test statistic. Turning raw data into a decision-ready number. The test statistic measures how far your sample result is from the hypothesized value, measured in standard errors. The general formula is the test statistic equals the sample statistic minus the hypothesized value divided by the standard error of the sample statistic. For a test about the population mean, this becomes x bar minus mu0 divided by the standard error. If sigma is known, the standard error is sigma over root n, and you get a z-statistic. If sigma is unknown, you use s over root n, and you get a t-statistic. The numerator tells you how far your sample mean is from the hypothesized value. The denominator standardizes that distance by the precision of your estimate. A test statistic of 2 means your sample mean is 2 standard errors away from the hypothesized value. A test statistic of 0.5 means it is only half a standard error away. The larger the test statistic in absolute value, the stronger the evidence against the null hypothesis. The decision rule compares the test statistic to critical values. The critical value is the threshold that separates the rejection region from the fail-to-reject region. For a two-tailed test at alpha equals 0.05, the critical z-values are plus and minus 1.96. If your test statistic falls outside this range, beyond plus 1.96 or below minus 1.96, you reject the null. If it falls between negative 1.96 and positive 1.96, you fail to reject. For a one-tailed test at alpha equals 0.05 in the right tail, the critical value is plus 1.645. If your test statistic exceeds 1.645, you reject. Notice the connection to confidence intervals. The critical values for a two-tailed hypothesis test at alpha are the same reliability factors used for a 1 - alpha confidence interval. If the hypothesized value falls outside the confidence interval, you reject the null. If it falls inside, you fail to reject. Confidence intervals and two-tailed hypothesis tests are two sides of the same coin. Let me work through a complete example. A fund manager claims his average annual return exceeds 10%. You collect a sample of 36 years of returns. The sample mean is 11.5%. Population standard deviation is 6%. Test at the 5% significance level. Step 1. Set up hypotheses. H0 says mu is less than or equal to 10%. H sub A says mu is greater than 10%. This is a one-tailed right-sided test because the manager claims returns exceed 10%. Step 2. Calculate the test statistic. Z equals 11.5 minus 10, divided by 6 over the square root of 36. The numerator is 1.5%. The denominator is 6 divided by 6, which is 1%. Z equals 1.5 divided by 1, which is 1.5. Step 3. Find the critical value. For a one-tailed test at alpha equals 0.05, the critical Z is 1.645. Step 4. Compare. 1.5 is less than 1.645. The test statistic does not exceed the critical value. Decision: fail to reject the null hypothesis. There is not sufficient evidence at the 5% level to conclude that the fund manager's average return exceeds 10%. The 11.5% sample mean could plausibly have come from a population with a mean of 10% or less. Part 3. Type 1 and Type 2 errors. The 2 ways a hypothesis test can get it wrong. A Type 1 error occurs when you reject a true null hypothesis. You conclude there is an effect when there actually is not one. In the courtroom analogy, this is convicting an innocent person. The probability of a Type 1 error equals alpha, the significance level. If alpha is 5%, there is a 5% chance of wrongly rejecting a true null. A Type 2 error occurs when you fail to reject a false null hypothesis. You conclude there is no effect when there actually is one. In the courtroom, this is acquitting a guilty person. The probability of a Type 2 error is denoted beta. Beta is harder to calculate because it depends on the true value of the parameter, which you do not know. Here is the trade-off. If you lower alpha, reducing the risk of Type 1 error, you increase beta, the risk of Type 2 error. Being more conservative about rejecting means you will miss more true effects. The only way to reduce both errors simultaneously is to increase the sample size. The power of a test is 1 minus beta. Power is the probability of correctly rejecting a false null hypothesis. In other words, if the null is actually wrong, power tells you how likely you are to detect that. High power means the test is good at finding real effects. Low power means the test might miss real effects even when they exist. What increases power? First, increasing alpha. A higher significance level makes it easier to reject, which increases power but also increases Type 1 error risk. Second, increasing the sample size. Larger samples reduce the standard error, making it easier to detect departures from the null. Third, the true parameter being far from the hypothesized value. A larger true effect is easier to detect. The CFA exam expects you to know that power equals 1 minus beta, and that increasing sample size increases power without increasing Type 1 error risk. That is why sample size is the preferred way to increase power. Part 4. P-values. The most misunderstood concept in all of statistics. The p-value is the smallest significance level at which you would reject the null hypothesis. Equivalently, it is the probability of obtaining a test statistic as extreme as or more extreme than the one you calculated, assuming the null hypothesis is true. Let me make this concrete. In our fund manager example, the test statistic was z equals 1.50. The p-value for a one-tailed test is the probability of getting a z-value of 1.5 or higher if the null is true. Looking up z equals 1.5 in the standard normal table, the area to the right is 0.0668. The p-value is 6.68%. The decision rule with p-values is simple. If the p-value is less than alpha, reject the null hypothesis. If the p-value is greater than or equal to alpha, fail to reject. In our example, the p-value of 6.68% exceeds alpha of 5%. So we fail to reject, same conclusion as before. But notice this. If we had used alpha equals 10% instead, we would reject, because 6.68 is less than 10. The p-value tells you exactly where the evidence stands, without committing to a single alpha. A critical exam trap about p-values. The p-value is not the probability that the null hypothesis is true. Many candidates make this mistake. A p-value of 6.68% does not mean there is a 6.68% chance that the fund manager is not adding value. The p-value assumes the null is already true and tells you how surprising your data would be under that assumption. It is the probability of the data given the hypothesis, not the probability of the hypothesis given the data. Here is an analogy. If I assume this coin is fair and then flip it 10 times getting 10 heads, the p-value tells me how unlikely 10 heads in a row is for a fair coin. It does not tell me the probability that the coin is fair. For that, you would need Bayesian statistics, which is a different framework entirely. On the CFA exam, if a question asks what a p-value means, reject any answer that says it is the probability that the null is true. The correct answer always describes it as the probability of the observed result, assuming the null is true. Part 5. Specific test statistics. Which test to use for means, variances, and equality. The z-test and t-test for a single population, mean, follow the same decision tree from the confidence intervals lesson. If the population is normal and sigma is known, or if n is large and sigma is known, use the z-test. If the population is normal and sigma is unknown, or if n is large and sigma is unknown, use the t-test with n-1 degrees of freedom. For the CFA exam, remember that when n is large, the z and t distributions are nearly identical. So with large n, the choice between z and t makes little practical difference. But the exam still expects you to choose correctly based on whether sigma is known or unknown. When the population is not normal and n is small, you cannot use standard z or t tests. You would need non-parametric methods, which the CFA Level 1 curriculum does not cover in depth. The exam will tell you either that the population is normal or that n is large, guaranteeing you can use one of the standard tests. The chi-squared test is used for testing a hypothesis about a single population variance. The test statistic is chi-squared equals n-1 times s squared divided by sigma 0 squared, where s squared is the sample variance and sigma 0 squared is the hypothesized population variance. The chi-squared distribution is not symmetric like the normal or t distributions. It is right-skewed, bounded below by 0, and its shape depends on degrees of freedom. As degrees of freedom increase, it becomes more symmetric. For a two-tailed test, you need both an upper and lower critical value because the distribution is not symmetric. The critical values are not equidistant from the center, unlike the z or t tests. When would you use this? When testing whether a portfolio's return variance equals a benchmark value. For example, does this bond fund's variance equal the variance of the aggregate bond index? The F-test compares two population variances. The test statistic is F equals S1 squared divided by S2 squared, where S1 squared is the larger sample variance and S2 squared is the smaller sample variance. By convention, you put the larger variance in the numerator so that the F statistic is always greater than or equal to 1. The null hypothesis is that the two population variances are equal. Sigma 1 squared equals sigma 2 squared. The F distribution has two sets of degrees of freedom. The numerator degrees of freedom is n1 minus 1, where n1 is the sample size for the group with the larger variance. The denominator degrees of freedom is n2 minus 1. When would you use the F-test? When comparing the risk of two portfolios. A portfolio manager claims their fund has the same volatility as a benchmark. You test this by comparing the sample variance of the fund to the sample variance of the benchmark. Let me give you a quick decision tree for the exam. Testing a population mean. Sigma known, use z sigma unknown, use t with n-1 degrees of freedom. Testing a single population variance. Use chi-squared with n-1 degrees of freedom. Testing equality of two variances. Use F with n1 minus 1 and n2 minus 1 degrees of freedom. Testing equality of two means with independent samples. Sigma known for both, Use Z sigma unknown for both but assumed equal. Use pooled T sigma unknown and not assumed equal. Use T with adjusted degrees of freedom. This decision tree covers virtually every hypothesis test question on the CFA Level 1 exam. The exam always provides enough information to determine which test applies. The key signals are the words variance, two populations, known, unknown, and the sample sizes. Part 6. Statistical significance versus economic significance. Why statistically significant does not always mean important. A result can be statistically significant but economically meaningless. Suppose you test whether a trading strategy earns excess returns. With a huge sample of 10,000 observations, you find a statistically significant average excess return of 0.01% per month. The Z-statistic is 3.2, well beyond the critical value, highly significant statistically. But 0.01% per month is 0.12% per year. After transaction costs of, say, 0.5% per trade, this strategy loses money. It is statistically significant, but economically insignificant. The reason is that with very large samples, even tiny deviations from zero become statistically significant because the standard error, sigma over root n, gets very small. A tiny effect divided by a tiny standard error produces a large test statistic. The CFA curriculum emphasizes that both statistical and economic significance must be considered. Always ask, even if this result is statistically real, is it large enough to matter in practice after costs? The exam tests this as a conceptual question, not a calculation. Part 7. CFA practice questions. 5 exam-style questions with full wrong answer analysis. Question 1. An analyst tests whether a portfolio's mean return differs from 12%. The sample of 50 observations has a mean of 13.2% and a population standard deviation of 4%. At the 5% significance level, the analyst should take a moment to work through this. The answer is a reject H0 because Z equals 2.12 exceeds 1.96. The test statistic is 13.2 minus 12, divided by 4 over the square root of 50. The numerator is 1.2. The denominator is 4 divided by 7.07, which is 0.566. 1.2 divided by 0.566 equals 2.12. This is a two-tailed test because the hypothesis says differs from 12%, not greater than or less than. The critical value for a two-tailed test at alpha equals 0.05, is plus or minus 1.96. 2.12 exceeds 1.96, so we reject. If you chose B, you used the 99% critical value of 2.575 instead of the 95% value of 1.96. Always match the critical value to the stated significance level. If you chose C, you made 2 errors. You miscalculated the test statistic as 1.5 instead of 2.12, and you used the one-tailed critical value of 1.645 for what is a two-tailed test. Question 2. A type 2 error is best described as. Think carefully about each option. The answer is B, failing to reject a false null hypothesis. A type 2 error means you conclude there is no effect when there actually is one. The null hypothesis is wrong, but your test failed to detect it. The probability of this error is beta. If you chose A, rejecting a true null hypothesis, that is a type 1 error, not type 2. Type 1 is the false positive, concluding there is an effect when there is not. A quick memory aid. Type 1 is the error of commission, acting on a false signal. Type 2 is the error of omission, failing to act on a real signal. If you chose C, rejecting a false null hypothesis, that is not an error at all. Rejecting a false null is the correct decision. That is what power measures. Power equals 1 minus beta, the probability of correctly rejecting a false null. C describes success, not error. Question 3. Which of the following most likely increases the power of a hypothesis test? Choose carefully. The answer is B, increasing the sample size. A larger sample reduces the standard error, sigma over root n. A smaller standard error means the test statistic is more sensitive to departures from the null. You are more likely to detect a real effect, which is exactly what power measures. If you chose A, decreasing the significance level, that actually decreases power. Lowering alpha means you require stronger evidence to reject. You are being more conservative, which means you will miss more real effects. Lower alpha reduces type 1 error, but increases type 2 error, and power equals 1 minus type 2 error. If you chose C, decreasing the sample size, that decreases power for the same reason B increases it. Smaller n means larger standard error, means less sensitivity. This is why increasing sample size is the preferred way to increase power. It increases power without increasing the risk of type 1 error. The only cost is the expense of collecting more data. Question 4. An analyst obtains a p-value of 0.03 for a two-tailed hypothesis test. Which of the following is the most accurate interpretation? Read each choice carefully. The answer is B. The null would be rejected at the 5% level, but not at the 1% level. A p-value of 0.03 means you would reject the null at any significance level above 3%. 5% is above 3%, so you reject at 5%. 1% is below 3%, so you fail to reject at 1%. If you chose A, there is a 3% probability that the null is true. You fell into the classic p-value trap. The p-value is not the probability that the null is true. It is the probability of observing data this extreme if the null were true. These are very different statements. If you chose C, 97% probability the alternative is true, this is the same trap from the other direction. 1 minus the p-value is not the probability of the alternative. The p-value framework does not assign probabilities to hypotheses. It only tells you how surprising your data would be under the null assumption. Question 5. A researcher finds a statistically significant excess return of 0.02% per month for a strategy using a sample of 20,000 monthly observations. After accounting for transaction costs of 0.1% per trade, the strategy most likely. Think about this. The answer is B, not economically significant because costs exceed the excess return. The excess return is 0.02% per month, which is 0.24% per year. But transaction costs are 0.1% per trade. Even one trade per month wipes out the entire excess return and then some. Statistical significance came from the enormous sample size of 20,000. With n equals 20,000, the standard error is tiny, so even a 0.02% effect appears significant. But in the real world, this effect is too small to profit from after costs. If you chose A, you assumed that statistical significance implies economic significance. This is exactly the error the CFA curriculum warns about. Statistical significance tells you an effect is probably real, not that it is large enough to matter. If you chose C, you do not need to know the significance level to assess economic significance. Economic significance depends on the magnitude of the effect relative to costs, not on the p-value. Here is your complete hypothesis testing cheat sheet. Every formula, every decision rule, every error type in one place. Pause here to study each item. That is hypothesis testing for the CFA Level 1 exam. You now understand how to structure a hypothesis test, calculate test statistics, choose between z, t, chi-squared, and f distributions, interpret p-values correctly, and distinguish statistical from economic significance. In the next lesson, we tackle linear regression. You will learn how to model the relationship between two variables, test whether that relationship is statistically significant, and make predictions using the regression equation. If this lesson helped you, subscribe and turn on notifications so you do not miss the next one. CFA Exam Mastery. Let us pass this exam.